Welcome, everyone. I am Dr. Kevin Woods presenting the second article in my climate series titled Analytical Modeling of Atmospheric Heat Absorption and Emission. My expertise is in thermodynamics and heat transfer, which is key to determining temperatures related to climate. The goal of this work is to enable the average scientist and engineer to model climate mechanisms using software such as Microsoft Excel. This article calculates atmospheric heat absorption and emission. Earth's surface emits heat, majority of which is absorbed by gases in the atmosphere, and this heat is re-radiated by the atmosphere into space and back towards the Earth's surface. The figure shows the absorption spectrum for solar and heat radiation by gases in the atmosphere. Atmospheric heat absorption occurs from a wavelength of about 2 microns to about 70 microns as shown by the red box. This is the range evaluated in the article. The range of about 8 microns to 14 microns is known as the atmospheric window, allowing about 15% of heat from the surface to reach space, while 85% is absorbed by the atmosphere. Water vapor's effect is shown in the box. The absorption from water vapor varies with concentration. For Earth, the concentration ranges from about 10 parts per million in polar regions to highs around 5,000 parts per million in tropical regions. The variation in the absorption by water vapor affects the influence of other gases such as carbon dioxide, ozone, methane, and nitrogen oxides. There are over 1 million absorption lines from these gases. Here is carbon dioxide's absorption bands overlapping with water vapors. The influence of the left band is dependent on the temperature from the emission spectra. Here is the influence of methane. The left band has no influence because it is outside the emission spectra. To sum up, heat emitted by the surface is absorbed by gases in the atmosphere, and these gases re-radiate the heat towards space and down towards the surface. This problem is difficult due to many variables including absorption overlap by different gases. However, this presentation will develop the mathematics to model this atmospheric heat absorption and will use the absorption spectrum to estimate atmospheric heat emission. The modeling begins with the first order differential equation equating the change in intensity of radiation with altitude to the absorption of the radiation at the given altitude. The absorption coefficient determines how much of the radiation is absorbed. The absorption is divided into two factors, the monochromatic absorption coefficient, kappa, and the particle density, rho. For a single absorption line denoted by the subscript I, kappa is calculated using a model for pressure broadening from an absorption line to an absorption distribution. The parameters in the pressure broadening are as shown. The pressure broadening half-width is expanded to the following equation related to pressure and temperature. The broadening mechanism is broken into two parts with air influence and self-influence. The air is the effect from different molecules, while the self is from other molecules of the same substance. A simplification of the pressure broadening assumes the total pressure is much larger than the partial pressure of the absorbing substance, that the temperature doesn't deviate from the reference temperature significantly, and that N sub air is approximately 0. The result is a simplified parameter of air pressure broadening times total pressure. Assuming the pressure shift of the absorption line wave number is 0 and the molar concentration of the absorbing substance is an ideal gas, the equation simplifies. Here's the simplification. The pressure with altitude is determined with a force balance as shown here. The parameter g is the gravitational constant, while r and TAV will cancel later on, but are the universal gas constant and average atmospheric temperature. The equation becomes a function with an exponential decay in the numerator and denominator. Up to now, the analysis was for a single absorption line, but all absorption lines must be summed to yield the total absorption at a given wave number. Integrating both sides of the function yields a natural logarithm on the left and an integral simplified using the following u substitution and parameter c1. Note r times TAV cancels out. Replacing the constant with c2, the equation becomes as shown. Evaluating the exponential from the left side of the equation yields a summation of natural logarithms in the exponent. The summation becomes a product and the exponent cancels with the natural logarithm. This yields the following solution for the atmospheric heat absorption for each wave number. The ratio compares the intensity of radiation exiting the atmosphere to the radiation emitted at the surface. This is the transmission through the atmosphere. So the absorption is 1 minus this ratio. Now remember, the assumed concentration for all substances was constant with altitude. However, water vapor changes significantly in the atmosphere from thousands of parts per million to tens of parts per million in the upper atmosphere. The concentration variation is modeled using a simple exponential with altitude. The factor beta determines the change of concentration with altitude. Using the Clausius-Clapeyron equation, we can estimate for beta. The estimate is shown where phi is the lapse rate, delta H is the latent heat of condensation, and T sub 0 is the temperature at the surface. One way to integrate the variation of water vapor concentration into the model is by assuming beta equals the atmospheric pressure exponent, 2g over RT/AV. Comparing to the Earth average and equator concentration profiles, the assumption is pretty accurate, especially for the equator. The assumption in the previous section follows the non-condensing line at the top. It is evident that the new assumption is more accurate. Integrating this into the differential equation from before, it's separated into water vapor and non-condensable substances. The subscript J is for water vapor absorption, and I is for all other non-condensing substances. And the exponential decay of concentration is integrated. Solving yields the following absorption equation. Note the factor B1 and B2 are similar to C1 and C2 from the previous section. Another consideration is the surface radiation is not all radiated vertically, but rather in all directions. The heat emission from the surface through the atmosphere assumed a vertical emission. However, heat emission is diffuse with each photon following a path S, given by a specific direction theta. The path length S is longer than Z, meaning additional absorption occurs. The concentric circles show the increase in the view factor from a differential area at the surface with theta. The view factor equation is given by f sub 1 dash 2. Multiplying by the path length 1 over cosine theta and integrating yields an average photon path length of 2. This means the average path length of a photon is twice the vertical distance through the atmosphere. The only change in the absorption equation is for the factors B2 and C2, which are doubled, causing the 2 on the bottom to cancel. Finally, we need the absorption line data to evaluate the absorption spectrum and deduce an overall atmospheric heat absorption. The HYTRAN database is the source of the absorption line data for the article. There are over 1 million absorption lines for atmospheric gases. To simplify, the million are rank ordered and reduced to the 10,000 strongest absorption lines. These 10,000 include the strongest 100 to 1,000 for each substance considered. The absorption spectrum is as shown in the solid black line for wavelengths from 2 microns to 30 microns. Above 30 microns, the absorption is 100%. Below 2 microns, the absorption spectrum is irrelevant due to the Planck distribution being 0. The overall atmospheric heat absorption is 83.9% at the given temperature. The spectrum is broken down into each component. It is obvious that water vapor is most significant, with carbon dioxide being next and ozone and methane playing smaller roles. Comparing each component to the distribution from before shows good agreement. And the same is true for the overall absorption spectrum. The assumption is that atmospheric absorption equals emission. However, this assumption is inaccurate. To understand why, we need to evaluate the Planck distribution for the surface at 287 Kelvin compared to the distribution for the atmosphere at 265 Kelvin. The overall atmospheric heat absorption is determined by applying the surface Planck distribution on the absorption spectrum. The overall atmospheric heat emission applies the atmospheric Planck distribution on the absorption spectrum. The overall absorption is 83.9%, while the overall emission is 85.3%. It is evident that these are not exactly equal, but may be assumed so for modeling purposes. The goal of this model was to enable an average scientist to generate a general atmospheric heat absorption curve for the atmosphere with varying concentration of substances. One of key interest is the effect of CO2. Here's the effect from CO2. The y-axis is atmospheric heat absorption, while the x-axis is surface temperature, which determines the concentration of water vapor in the atmosphere. The CO2 concentration varies from 0 parts per million to 1,000 parts per million. Note the logarithmic nature of the change in absorption. Also of note is the increase from 0 parts per million to 100 parts per million is nearly twice the increase from 100 parts per million to 1,000 parts per million. This is a key concept in climate modeling because the influence of adding carbon dioxide to the atmosphere has diminishing effect on heat absorption. The carbon dioxide concentration in the last million years have ranged from about 180 parts per million to 420 parts per million. Here is a representation of surface temperature relative to surface area of the Earth. The median is shown here, and the equatorial, temperate, and polar zones are as shown. What this means is the effect of CO2 varies with location on Earth. To be noted is this distribution is average annual temperature. Daily minimums in polar regions reach about 220 Kelvin or about -50 degrees Celsius, and daily maximums in equatorial regions reach about 310 Kelvin or about 40 degrees Celsius. The best model includes the entire atmospheric absorption equation with more than 10,000 absorption lines. However, for the general scientist interested in modeling climate, an approximate model assuming the absorption and emission are equal is as shown. The model captures the logarithmic effect of concentration between 100 and 1,000 parts per million. For 10 to 100 parts per million, the model changes to the following equation. The two major changes are the two coefficients on the denominator. And for 1 to 10 parts per million, the model changes again as shown. Again, the two coefficients on the denominator change. In summary, the main component of atmospheric heat absorption is water vapor. Carbon dioxide's influence changes with location and is non-linear with concentration. The main outputs of this presentation are the analytical absorption model and the approximate model for the average scientist. Note the two coefficients are replaced with A and B in this equation. My future work focuses on modeling more parameters relating to Earth's climate to integrate into a previously published climate model for the Earth. However, the goal is to provide credible evidence validating or invalidating climate claims. I'd like to acknowledge the HyTran website for the absorption line data utilized in the model. The database is available at hytran.org. For the entire article, please go to prosejournals.com. Thank you and please subscribe and click for notifications.